All right, what can I do for y'all? There's a seat right here. There's a seat over there. Make it happen. Okay, so before we even start talking about atoms and elements here, let's just take a second to introduction to general chemistry. All right, and really what I want to do is get us thinking about, why are you here? All right, I'm pretty sure if I ask most of you why you're here, you're going to tell me because your counselor told you that you had to take this course, and you're trying to check that box and move on with your life, right? Okay, great. I'm going a little more meta than that, right? So my real question is, why do we bother to learn chemistry in the first place? Every high school and college pretty much across the entire country, across the world, teaches chemistry as one of the three main branches of science, along with physics and biology. So why? Why is chemistry one of those three main branches here? All right, so first of all, let's tackle what those three main branches are and kind of what they're doing differently. So first of all, we have physics. In terms of scale, physics is looking at the very smallest aspects of our universe, right? Really zooming in and trying to figure out what the fundamental rules that govern matter and energy are. Okay, matter is everything around us that we see, everything that we interact with. There's also this very elusive quantity that we'll talk about that's very important for the universe, what's called energy, and we'll see how these two are closely related as we go in this course. But physics is really that deep dive study of the very most fundamental rules that govern matter and energy. All right, we're going to leave a little bit of space here, because if we zoom now all the way out, now all of a sudden we're talking about biology. Okay? Biology is a study of science on a much larger scale than physics, and it's specifically looking at how do living systems function. Very practical question, right? We are all living organisms wanting to know how the rest of life operates. That's definitely a very good application of science. Chemistry sits right in the middle. All right. In chemistry, we're now asking just, what is matter? All right, what is matter? What are its properties? All right, and then most interestingly, how does one form get converted to another? All right, the process that we now know is a chemical reaction. All right, so in terms of scale, physics is looking at the very teeny tiniest. Biology, now we're kind of zoomed out looking at cells, living organisms. All right, you can zoom out even further, talking about environmental biology, stuff like that. All right, but physics kind of sits in the middle. It's this intersection between physics and biology. All right. And in terms of why we study chemistry, well, chemistry actually exists long before the field of chemistry has existed. Or rather, humans have been harnessing the power of chemistry for a very long time. If you think all the way back to like Neanderthal times, the creation of fire, that was really humans harnessing a chemical reaction for the first time. A fire is just taking a fuel source of carbon and reacting with oxygen to produce carbon dioxide, water, and a bunch of heat. Now, did they know that they were doing a chemical reaction? No, not at all. I'm sure they thought it was basically magic, right? But we now come to understand that as a chemical reaction that follows these very closely, very tight rules of how chemical reactions actually occur. Even more beyond that, right? So we get to ancient Egypt. of course they're using fire and all that sort of stuff, but they also like their makeup and their dyes for their clothing, these things that are very fundamental to humans, to look good, to smell good. And they were doing chemical reactions to create these dye molecules. They were making perfumes by extracting good smelling compounds from fruits and from flowers. All these chemical techniques that we use nowadays. The Indians are famous for having developed this technique of purifying zinc through this distillation process. Something that's like this very kind of clever thing that we still do in the lab today, this distillation technique. They were able to take a rock and get some pure zinc metal from it that then helped them develop brass, this nice new strong metal that carried on this new age of human development, right? So before the subject of chemistry existed, human beings have been harnessing chemistry for a long time. And so why do we bother studying it? Because the bottom line is every civilization, all right, since the dawn of time, they have needed to understand how to extract, how to purify, combine, or otherwise transform matter. Okay? A lot of people will credit like the birth of chemistry to the scientific revolution that happened in Europe, and that did make a very big turning point towards this more quantitative approach to science, right? Taking numerical measurements and all this data-backed approach. So don't get me wrong, that was very important, but again, chemistry has existed long since before that. All right, or rather its importance in human history. Okay. So where are we going to start with our discussion of chemistry? Well, one of the most fundamental things that those early chemists established was this idea of the atomization of matter. The idea that all matter around us is made up of these teeny tiny building blocks known as atoms. Okay, our atoms are our building blocks of matter. Say of all matter. Okay, all right, hold on a second. Let me pause for dramatic effect. I gotta get my image ready. Okay, my bad. Okay, so the first thing that we need to do is we need to look at the anatomy of an atom. All right, what do atoms actually look like? Okay, our atoms are composed of three what are called subatomic particles. All right, if we're going to pick this word apart here, that's a big scary word, subatomic. What do we think we mean there? Also, I can't spell particles. Right, so let's pick it apart. First of all, we got the word atomic in there. So what do we think that means? Corresponding to atoms. So then what does that prefix sub mean? Smaller than an atom, right? So again, these are the building blocks of an atom, these three particles here. Okay, so if we're looking at an atom, it's got these two main parts. It's got this middle part here, this core, and then it's got this outer part here, okay? So the middle part is what we call the nucleus. All right, our nucleus of our atom here is where two of those three subatomic particles live. We have it represented in blue here are our protons and I guess I can actually represent it in blue just to be clear. We have our protons. And represented in red, we have our neutrons. All right, these both live inside of that nucleus. All right, outside the nucleus, we have our what we call electron cloud. And our electron cloud is where our third subatomic particle, our electrons, live. All right, so these are our three subatomic particles here: protons, neutrons, electrons. Protons and neutrons are in the nucleus. Electrons are outside the nucleus in what we call this electron cloud. Now, to be clear, the electron cloud is actually mostly empty space. All right, with those electrons flying around inside. All right, I imagine them as little lightning bolts kind of zipping around the outside space there around that nuclei. All right, the other thing that I want to note about this picture here is it's really sort of misleading in terms of the relative size of the nucleus and that electron cloud. The nucleus in this picture here is way bigger than a nucleus actually is. A nucleus is incredibly, incredibly small. The atom is actually made up mostly of that electron cloud, made up mostly of that empty space with those electrons traveling around in it. The nucleus is very teeny tiny in the middle of that atom. All right, so let's just note here, this picture is not to scale. All right, the nucleus is very, very small inside that atom. Okay, so again, atoms actually are composed mostly of empty space, that electron cloud, with those protons and neutrons kind of crammed in the middle there. Okay, so here's our anatomy of our atom here. And so again, all matter around us is made up of these atoms here. All of these atoms are consisting of these same three subatomic particles. Okay, let's talk a little bit more about these subatomic particles. All right, so again, we have our three, our protons, our neutrons, and our electrons. And if you're really trying to like dive in deep and figure out the properties of these different subatomic particles, that's really for a physicist sort of topic, right? So chemists are more concerned with the things that atoms do, not the individual subatomic particles themselves, but there are three important things that we need to know about these subatomic particles, all right? So we're gonna make a little cheat sheet chart here. The first we've already talked about, which is where they live in our atom. Okay, so first, where do you live? All right, so given what we just discussed, everybody take a second, fill out this chart here. Where do these subatomic particles live in our atom? All right, so our protons and our neutrons, where are they going to live? The nucleus. All right, and what about our electrons? They live outside that nucleus in those electron clouds. Okay, two other fundamental properties of these particles that we need to know. First is the mass of these particles. All right, so first of all, we're going to talk about mass quite a bit today when we start talking about units and different units that we use to measure mass. Here in the US, we use pounds. If you're, most of the world uses the metric system, so grams or kilograms. But these are essentially a measure of how much something weighs, which is not really strictly true. Your mass is the same here on Earth as it is on the moon, but your weight is different because of that force of gravity. So weight is really your mass, but then taking into account the force of gravity. But guess what? We're going to be only talking about Earth chemistry here, all right? So when we think about mass, we can really roughly just say, chalk it up to how heavy or how light something is, right? That's the mass of something. And these particles are very different in their mass. It turns out that protons and neutrons are both about 1 AMU, or 1 atomic mass unit. This is probably a unit of mass that you haven't heard of before. You've probably heard of grams and pounds. Atomic mass units are used to measure stuff that's really teeny tiny small. We can always convert from AMUs to grams or to pounds, right? We can convert between any mass units, but this is a new one here, and it's because we're talking about something that is ridiculously, ridiculously small, all right? An electron is very different. An electron has a mass of 0.00055 AMU. So you can see quite a bit less massive than our protons and our neutrons, to the point where, practically speaking, we often think of electrons as not having much mass at all, right? So this is such a tiny number, we can say it's about 0. All right, strictly speaking, it's not perfectly 0, but it's pretty freaking close, especially in comparison to a proton and a neutron, which means if I'm holding an atom in my hand here, where does all of that mass of that atom live? In the nucleus, right? That outer electron cloud, which is most of that atom, doesn't actually have much mass associated with it. All the mass is in that teeny tiny little core, the nucleus of that atom. Okay, there's another fundamental thing that we need to talk about with regard to these particles, and that is the charge of these particles. Charge is something super bizarre. It's just another force that we see falling out of physics. For our purposes, all we need to remember is that opposites attract and like forces repel, right? That's sort of all we need for our chemistry course here. Again, these particles have very different charges. Protons have a charge of +1. Whereas neutrons are neutral. They do not have any charge associated with them. All right, and then our electrons, they have that opposite -1 charge associated with them. Okay, cool. So these, again, what are we, if we're going to sort of boil down what we just talked about, the bottom line is all matter consists of atoms, and atoms consist of these 3 subatomic particles, protons, neutrons, and electrons, and these are these 3 properties of these particles that we got to know, okay? Okay, so now we're going to take a look at our constants page for this chapter here. Specifically, we're going to be taking a look at this periodic table, okay? So this is our periodic table. Again, this is the one that we're going to be using throughout this course. Before we sort of dive in and figure out what the heck we're looking at, what is a periodic table? A periodic table is just a summary of all the different atoms that human beings have discovered up until this point, right? So if I were to hand you an atom, you could put it into one of these boxes here. It's going to fall into one of these categories. Every atom that we've discussed is one of these categories here, one of these what we call elements, all right? So let's kind of zoom in and pick these apart. Each one of these tiles has these same 4 pieces, really 5, but I'm going to kind of ignore one until we get later in the course. 4 important pieces of information, okay? So first of all, at the very top, we simply have the name of that element. All right, here's our element name. Okay, the next number down, the big number up top, the big whole number is going to be our atomic number. All right, and then we have our chemical symbol here. All right, so this element's name is boron, But basically, scientists are really lazy and we love a shorthand. So every time we want to talk about boron, we don't want to have to write the word boron, so that's when we used its symbol here. We use that uppercase letter B, and everybody knows what element we're talking about. Every element has a unique chemical symbol. All right, and then the one at the bottom here, the next one down, this is the atomic mass. And we're not going to talk too much about atomic mass at the very beginning of the course, but it's going to be really important as we go throughout the course, these atomic masses here. And then we see these little numbers down at the bottom, and I'm going to punt on explaining what that is until we get to that relevant chapter, which will be about a month and a half or so. So we got those little numbers. They will become important later on. If you're curious, they're what are called Pauling electronegativity values, but we'll go through and define all that later on in the course here. So these are the big four categories that we need to pay attention to. Each element has a name, an atomic number, a chemical symbol, and an atomic mass. Okay? All right, so why is the periodic table arranged in this weird like staircasey thing? Why isn't it just a box? All right, so they kind of cleverly arranged the tiles on the periodic table here. So first of all, what we need to do is looking at this periodic table, we need to be able to cut it up and learn a few, like these elements are going to fall into different classes here, okay? So first of all, on yours, because it's not a color copy, it's a little hard to see, but everybody take a second and just note, you have this little staircase here that separates the two halves of our periodic table, okay? It's a little bit harder to see. You can kind of color it in if it's like a little gray blurry line on yours, but just note we have this little split. And this divides these two halves of our periodic table, okay? Everything located on the left half of our periodic table is what we call our metals. All right, so all these elements here located on the left half of this periodic table, rather the left half of our staircase, all right, and even the ones down here are considered to be metals. You can see the vast majority of elements that we've discovered are classified as metals. Everything on the other side of our periodic table, these are all our non-metals. They got real clever with the name. We got metals and then non-metals. All right, now it is a little bit more complicated. There's 1/3 class of elements that are like right on the line there, right in the line between metals and non-metals, such that they really have properties of both. And these are what are called our metalloids. And those are the elements that are touching the staircase. All right, these are all our metalloids here. Now, there are two exceptions to this rough cut that I just laid out here. First of all, you'll notice that I didn't highlight aluminum in purple. Aluminum, even though it's touching the staircase, is considered to be a metal. Okay? And we've all encountered, if you've ever used aluminum foil, that is pure 100% aluminum metal, and you can kind of convince yourself looking at it, it really looks like a metal, right? So yes, aluminum is considered to be a metal, not a metalloid, despite touching the staircase. And the other thing that's on the wrong side of the periodic table, and we'll see this a lot, is that teeny tiniest element that we have, hydrogen. Hydrogen, despite being to the left of that staircase, is still considered a non-metal. It has properties of a non-metal. Okay? So first things first, if I give you an element, you should be able to tell me if it's a metal, a non-metal, or a metalloid, all right, based on where it lives on the periodic table. Okay? Now, the hard part being, we cut this thing up, but of course on your exam, what are you going to be given? A blank periodic table. So you need to make sure that you know how to cut that up yourself. Y'all are free to mark up your copy of the periodic table as much as you want, but just note that on an exam, you're going to be given a fresh periodic table to go off of. Okay? All right, so the other reason that we designed that, I didn't design it, let me not take credit for that. The reason that the Russian dude back in the day designed the periodic table the way that he did is because all elements that live in the same column behave very similarly in terms of their chemical properties. And you don't even know what I mean by that yet because we haven't talked about any chemical properties. But when we do start talking about properties of these elements, we'll see that elements that live in the same column share the same properties. All right? So because of that, we have names for these different columns. All right? So all the way on the end here, starting at the back half, I'm going to get rid of these labels. This very last column of elements here. All right. Anybody know what these are? Yeah, these are our noble gases. Okay. First of all, they're all gases, so that's why they get the name noble gases. They get the name noble gases because they are the most unreactive of all the elements. You do not find them in compounds with other atoms. These atoms are always floating around by themselves. So for example, helium, I think we've all heard of helium. If you have a sample of helium, that helium atom is not going to bond with any other atoms, right? They're only all by themselves, all floating around. If we go next door, these are sort of the opposite. These are highly reactive elements here, and these are what are called our halogens. Okay, jumping to the other side, this first column here, and we're going to exclude hydrogen because we're going to only talk about the metals in this column here. These are our alkali metals. All right, and the family next door, second column. Kind of an obnoxiously similar name here. These are our alkaline earth metals. Okay, and then lastly, we got this entire block in the middle here. Turns out that all these elements here share quite a few properties together, so we lump them all together. These are what are called our transition metals. All right, now there are some families that we haven't named here. Some of them actually do have names, and I just don't care if you know them because they're not widely used. These are the 5 big categories that I expect you to know. Okay, we have our alkali metals, our alkaline earth metals, our transition metals, our halogens, and our noble gases. Okay, so given an element here, you should be able to tell me which family it belongs to. Okay, if I give you a chemical symbol or a chemical name, you tell me whether it's a halogen, a noble gas, a transition metal, et cetera, et cetera. All right, so let's go back to our blank periodic table here. And let's just practice this. I'm going to put down 2 elements. I want to know if it's a metal, non-metal, or a metalloid, and if it belongs to one of those special families, what special family does it belong to? All right. I'm going to give one the name chlorine, and the other one I'm going to give just the symbol. All right, so metal, non-metal, or metalloid, and what special family do they belong to? Everybody take a second, hunting around your periodic table. One of the things that you're going to realize is at the beginning, you don't know where any element lives on the periodic table, and then by the end of the semester, you're like, I can pick out oxygen blindly on that thing, all right? So, like, hunting around the periodic table is a skill that we're going to get as this semester goes on. All right, chlorine. Has anybody found chlorine? Let's see, raise a hand. Have you found chlorine here? All right, what's its atomic number? 17. Okay, great. So this is chlorine here. So what do we got? Metal, nonmetal, or metalloid? So this one's a nonmetal. And what special family does it belong to? It is a halogen. Okay, Na is the chemical symbol for which element? Sodium. What's sodium's atomic number? 11. So that one's over here now. And is that a metal, non-metal, or metalloid? We got a metal to the left of our staircase. And does it belong to a special family? This is our alkali metals. Cool. All right. Last thing with regard to our periodic table that we want to make sure to cover here, we talked about these subatomic particles, right? Protons, neutrons, electrons, and then we switched gears and we started talking about these elements. And we said that this was a summary of all the different atoms that humans have discovered, okay? So tying those two together in here, this atomic number here is a very special piece of information about the atoms that make up that element. Our atomic number is equal to the number of which subatomic particles? Does anybody know? The number of protons, all right? So the number of protons in that atom tells you which element that atom is. So first of all, what is this weird little symbol I did here? This is the symbol for protons, right? Let's see if we can reason why that would be the symbol for protons. So first of all, P for proton. And why does it have the little plus up there? Because protons are positively charged, right? So this is this little shorthand symbol that we use for protons, all right? And again, our atomic number is it tells you the number of protons that that atom has. Meaning that if I have an atom in my hand and that atom has 5 protons, I know that atom is a boron atom. Right? If I added an extra proton, it wouldn't be boron anymore. Now all of a sudden it would be a carbon atom, right? So the number of protons uniquely determines the element and uniquely determines the behavior of that atom as well. Cool. All right, so going back here. Whoops, not that. Okay, the next thing we're going to talk about are what are called isotopes. All right. Again, the number of protons is going to identify what your element is, right? So atoms with the same number of protons, that implies it's the same element. Okay, you add protons, you take them away. Can I not move that? Bummer. Let me just rewrite this. Okay, sorry. Again, the number of protons uniquely determines what tile on that periodic table we're talking about, what element we're talking about. All right? But if we remember, our nucleus of our atom isn't just composed of protons, there are also those neutrons in there as well. So isotopes, all right, these are defined as atoms that have the same number of protons, so same element, but they have a different number of neutrons. Whoops, but different. And we got a new little fancy symbol that we're going to make note of here. All right, to represent a neutron, we use that lowercase n with the 0 in the superscript. Why do we use the 0? Remind ourselves that they're neutral. Cool. Okay, so here we have 3 different isotopes, all right? Let's actually just let's do one by one here. kind of zoom in. All right, so first of all, let's figure out how many protons, neutrons, and electrons we have in this atom here. All right, how many protons do we see? 6. 1, 2, 3, 4, 5, 6. How many neutrons do we see? Also 6. And how many electrons? 6. Okay, so first of all, before we go on here, what element am I talking about? Carbon, right? And how do we know that it's carbon? Because we got 6 protons. Nothing else on this list matters at all in terms of determining what element we're talking about, just that number of protons. So in this case here, we can note that we are looking at a carbon atom. Let me move it a little bit higher. All right, let's look at another atom. And fill out the same 3 pieces of information here. Everybody take a second. Tell me how many protons, neutrons, and electrons we have. I guess I'll zoom in for you. We got 1, whoops. We got 1, 2, 3, 4, 5, 6 protons again. And we have now 1, 2, 3, 4, 5, 6, 7 neutrons. And 6 electrons. Okay, so now which atom am I holding in my hand here? Still a carbon atom, because again, we still have those 6 protons. So yes, we are still talking about carbon. These are now 2 distinct isotopes. So this is a pair of carbon isotopes. They have the same number of protons, but they differ in their number of neutrons. Okay? So if we're talking about a specific carbon isotope, we can't just use the name carbon, right? That tells us the 6 protons, but it doesn't tell us how many neutrons there are. So we have to add this other piece of information into the back half of this name here, all right? And this is what we call the mass number. The mass number of an atom is equal to its number of protons plus the number of neutrons. All right, and so if we're naming a specific isotope, we're going to use this format where we do the element name dash mass number. All right, so this atom here with its 6 protons and 6 neutrons would have a mass number of 6 plus 6, right? Number of protons plus number of neutrons. So this would be a carbon-12 atom. And what about over here? What would this one be? Carbon-13. Okay. And just a fun fact, these are the 2 major isotopes of carbon that we see in our universe. We are made up of a bunch of carbon, right? Carbon is one of those building blocks, one of those elements that are fundamental of life. All carbon out there is a mixture of carbon-12 and carbon-13. It turns out that there's way more carbon-12 than there is carbon-13, but we all got a little bit of that in us as well, right? Those 2 isotopes are mixed together. Cool. All right, now, next thing we're going to learn how to do. We have our chemical symbols. We know how to abbreviate the element carbon. We wanted to be able to do the same thing with our isotopes, so we want to talk about our isotope symbols. All right. So let's just stick with this example here of carbon-12. Rather, we got 6 protons, 6 neutrons, and 6 electrons. We said that was carbon-12. Now this would be the name. Now let's think about the symbol. Okay. So our symbol here, we're going to start with that chemical symbol for carbon. All right, so we got that uppercase C. If we look on our periodic table, carbon has that symbol uppercase C. So here's our chemical symbol. But again, that's not enough to determine which specific carbon atom we're talking about. So we're going to build that mass number into this symbol as well. That mass number is going to go in the upper left-hand corner. So carbon 12. All right, this is our mass number. All right, and we're also going to put the atomic number in the lower left corner here. Okay, and we know that carbon with its 6 protons has that atomic number of 6. This is a little bit of a redundant piece of information. By telling you it was carbon, I knew its atomic number is 6. But what we'll see, and we actually won't even see it until next semester, when we start talking about nuclear chemistry, it's a helpful little bookkeeping tool to keep that atomic number there. All right, so there's logic behind it. It is a little bit of a redundant piece of information at this point, but we'll see why it's useful next semester. Nonetheless, this would be our isotope symbol for this carbon-12 atom. All right, so then let's go ahead and finish it off our examples here. Again, we said that this was carbon-12. Everybody take a second, just finish off. Give me that symbol for carbon-13. All right, still carbon. Atomic number is still 6, but now it's got that mass number of 13. Cool. Okay, now up until now, all of our examples have had the same number of protons as they've had electrons. Now we're going to start playing with those numbers here, all right? And these are what are called ions. All right, our ions, these are just atoms, but they're atoms that have a net charge associated with them. All right, well, remember which 2 of our subatomic particles are the charged ones? Protons and electrons. So up here, does this atom have a net charge associated with it? No, because it's got the same number of protons as it does electrons. So same amount of positive charge as it has negative charge. Those cancel each other out, leaving us with a net charge of 0. All right? So in order to be an ion, this would have to be an atom that had a different number of protons and electrons. All right, so how does this happen? How does this little imbalance between protons and electrons happen? So first of all, if I have an atom, if I'm holding an atom in my hand, you're not really able to change the nucleus of that atom. If it's got 6 protons, it's going to keep having 6 protons. There's no way to easily add protons or to take protons away. But what we can do is add electrons or take electrons away pretty easily from our atoms. All right, so atoms they can either lose electrons All right, if it was neutral and I took away an electron, what would the net charge on that atom be, positive or negative? Yeah, if I took one of those negatively charged electrons away, now I have more protons than I do electrons, so this would give me a positively charged ion. All right, on the other hand, we can have atoms gain electrons. So if I start giving it more negatively charged electrons, this is going to leave a negatively charged ion. Okay. And we have some fancy terminology. We call positively charged ions cations, and negatively charged ions we call anions. All right, so we're going to use this terminology a bunch, cation, anion. It's kind of easy to get them flip-flopped here. So we have this stupid little phrase that's going to help us remember this here. All right, and that is that cations are positive. Hysterical, I know, because cats have paws. Cations are positive. There's a lot of things where I've realized that I can say one stupid little phrase and it's going to get stuck in your brain for the remainder of the semester. And I want everybody to be able to distinguish between cations and anions, so you're going to hear me say cations are positive until it's embedded in your brain and you can't get it out. All right? Cool. So now let's incorporate this into our discussion of what we've been doing up until now. All right. Let's say that we have an element that has 9 protons. Yeah, perfect. 9 protons, 10 neutrons, and 10 electrons. Based on what we've discussed up until this point, everybody take a second and give me the symbol, right? The isotope symbol for this element here. All right, so first of all, what element am I talking about? Fluorine, right? And what gives it away? Our number of protons. We got 9 protons. That means we're talking about element 9 on our periodic table. That's fluorine. What else do I need to include? That atomic number goes down here. What's going to go up top? That mass number. And what is the mass number for this particular atom? The number of protons plus the number of neutrons. That gives me a total of 19 for my mass unit. Okay, but let's think here. What would be the net charge on this? In this case, it's an ion here because it has a net charge. All right, how do I figure out my net charge on this ion? So if we want to treat it as a math problem, we can. Net charge would be the number of protons minus the number of electrons. All right, so if we did this for this particular example here, I have 9 protons. I'm going to subtract away 10 electrons. What does that leave me with? A net charge of -1. Okay, now you can treat it like a math problem, but I'm not going to give you this formula. If you think that the easiest way to approach this is to memorize this formula, then go for it. But I think that we can do this a much smarter way that doesn't require memorization. And that is to just take a step back and look and say, which one do I have more of? Protons or electrons? Electrons. So should I have a net positive or a net negative charge? Negative charge, right? So rather than trying to memorize a formula where we might accidentally flip things around and get the wrong answer, just take a step back. What do I have more of? Do I have more positively charged particles or more negatively charged particles, right? So yes, my net charge here is -1. Now we need to build that into our symbol, all right? For ions, we include our charge in the top right corner. Boom. So this is my net charge. We wouldn't put anything there if we were talking about a neutral atom, but if we're talking about an ion, we include its charge in the upper corner here. You could do this or have the actual value represented. If it's +1 or -1, the convention is to just use the sign itself, not actually include the value. All right? And then I say that, and unfortunately, obnoxiously for your isotopes homework, the only way that I could code it, I set out a little bit of a warning, is using this symbol right here, but going forward, we'll have like a different problem type and we won't have to include it, all right? Generally speaking, on an exam, either one's included, but again, this one's sort of considered to be the sleeker convention here. Okay, so then let's do the same thing here. Everybody's going to, I'm gonna tell you we have 12 protons, 13 neutrons, and now 10 electrons. Everybody take a second and give me the symbol of this compound, of this atom. All right, so first of all, what element are we talking about? Magnesium, so Mg, magnesium is the 12th element on our periodic table. And what would the mass number be? Our 12 plus 13 here gives us a mass number of 25, and I'm done. What's missing? That net charge. I have a net charge associated with this here. So it's actually not an atom, it's an ion. And what is my net charge going to be? Yeah, so I have a different, I have 12 protons and 10 electrons. So there's a difference of 2. But again, the question is, what's my sign here? Well, we'll just note we have more protons than we do electrons. So our net charge here is +2. Okay, again, in terms of convention of signs, there are certain people who believe somewhat strongly that we should do our symbols, rather our charges, as 2+ instead of +2. It drives me nuts. First of all, one's not more correct than the other. Both of them would be perfectly normal. You'll see both of them. And it drives me nuts because I was a math minor, and what the heck is 2+? No, we're gonna stick with this normal one here. This is how we're gonna be representing our ion charges going forward here. All right, really, I just had to pick one for our homework, and this is what I prefer, and so this is what we're gonna roll with here, okay? Cool. All right, so last thing that we're gonna do is we're basically gonna take everything that we just talked about and kind of roll it up into one here, and these are what I call these isotope table problems. Okay, and again, I like these because they summarize a bunch of the different pieces of information that we've been discussing here today. And hint, anytime I say I like a problem, that's a guarantee that you're gonna see it on an exam, right? If I'm like, ooh, I really like this problem, you should star it on your notes, like, oh crap, this one's definitely gonna come up, all right? So first of all, this is this table where we're just gonna summarize a bunch of different information about these isotopes. We learned how to name these isotopes. We can give this symbol. All right, we also talked about how we calculate the number of protons, number of neutrons, and number of electrons, as well as the mass number and the charge. All right, so what we're gonna do is make a table here, where for each isotope, we got all these different pieces of information. All right, and let's go ahead and do 3 examples here. Okay, so for example, the name of the game here is I'm going to give you certain pieces of information and you need to fill in the missing pieces of information, all right? So for example, if we have 28 protons, 30 neutrons, and 26 electrons, you should be able to fill in the rest of this table here, right? What's the name, what's its symbol, what's the mass number, and what's its charge? All right, and this is basically what we've been doing, but I'm going to throw up a few more difficult ones up here as well, where I'm giving you different pieces of information, other stuff's missing. Okay, so the first one, same examples that we were doing up here, right? Just presented in a slightly different format, but same idea in terms of how you're going to find this piece of information out. Number of protons tells me where to look on my periodic table. So I go to tile 28, that would be nickel, which I always spell wrong because it's EL, which drives me nuts, but whatever. And then we got to do the name dash mass number. So that means we got to calculate our mass number by adding the number of protons and the number of neutrons together to give us 58. All right. Lastly, in order to do our symbol, we're going to need to figure out what that net charge is. Sorry. Yours looked the exact same but slightly different. Sorry. In order to figure out what our net charge is, we need to look and see we have 2 more protons than we do electrons, giving us that net charge of +2. Okay? All right, so for the next one here, now it's the same game, but you're given different information than what you were given before, right? So now I'm going to have to figure out how many protons and neutrons I have, for example, what my mass number, net charge, etc. Okay, so first of all, lithium-7. I can start to do my chemical symbol here. This would be lithium. Mass number goes up top 7. And in the bottom right corner, I'm going to put, or bottom left corner, I'm going to put 3, because that's lithium's atomic number, which means I should also put a 3 where? Number of protons. Okay. In terms of my number of neutrons, how am I going to figure out how many neutrons I have? Because I know my mass number must be that 7. So let's go ahead, we can fill in mass number here. And importantly, up here at the top, we said that the number of protons plus number of neutrons equals our mass number, right? We're going to use the same 3 boxes. We're just going to have to rearrange our math problem here. Now we're going to do mass number minus the number of protons, giving us those 4 neutrons. All right, and lastly, what would the charge be? So this would be neutral. I got the same number of protons and electrons, so boom, neutral. All right, and then this one's all sorts of all over the place. All I'm given are the number of protons, a mass number, and a charge, and I got to fill in the rest here. All right, so first of all, number of protons is a big piece of information. It tells me where to look on the periodic table. What element are we talking about? Aluminum. And we must be talking about aluminum-26 because I know its mass number as well. So I can start my chemical symbol here. Okay. Now I get to my number of neutrons. And again, I'm going to have to use the relationship between protons and my mass number to get my number of neutrons. Right? So I'm going to take that 26 and subtract. I mean, just to be clear here, right? Mass number equals protons plus neutrons. Well, we can rearrange this equation here. Neutrons equals mass number minus number of protons, right? So just some simple algebra rearranging our definition of a mass number here. And that tells me that I have a total of 13 of those neutrons, right? 13 plus 13 gives me 26. Okay, so then how am I going to figure out my number of electrons? What pieces of information am I going to have to use? My protons and my charge, right? Because my number of protons and my number of electrons together equals our net charge. Okay, in this case, I have a positive net charge. So what should I have more of, protons or electrons? Protons. So that's how I know I will have fewer, or 10, electrons in this particular ion. And then the last thing I need to do so I don't get points off, what do I have to update here? That charge, right? Make sure to put your charge on your symbols, that charge of +3. Okay? So these are these isotope tables. I'm giving you certain pieces of information, and it's your job to go in and fill in the missing pieces of information on that table. Again, kind of summarizing what we've discussed about atoms and isotopes up until this point. Okay? I'm going to end things a little bit early here so that I can take attendance, and then again, we'll be meeting back at 2:30 for